Right, it's 1 o'clock. It's Thursday. It's time for the first Data Science Melbourne webinar of 2021. So welcome everyone. My name is Phil Briley. I'm the host of I'm the organizer of Data Science Melbourne, and also the presenter for today, where I'll be doing a talk. You just can see the slide. You've noticed I've subtly changed the title of the talk from, it's now called "What is Machine Learning Doing?", which I kind of realized was a better title once I went through my presentation. Okay, so up to 100 participants now, 101, so they're all coming in. So I'll probably start in 2 minutes, but first, a couple of announcements. Have we got just, is Monica here? Can you give me a thumbs up, Monica, if you're around? Okay, yeah, Monica's there, good. So, love the technology. Okay, so 100 attendees, they'll creep in over the next few minutes when I actually start the presentation. So we'll start off with a bit of intro, a bit of background. So, as I said, this is a Data Science Melbourne Meetup Group presentation, the first one of 2021, and I'm your kind of host and presenter at the same time. So I've got a lot of complicated things to do here, so bear with me. As usual, thanks to our sponsors. We've got like 4 universities in Melbourne backing this group, and a few companies, which we're really thankful for. Really appreciate the help. Without knowing people kind of want to keep this group going, we just won't do it. So we need kind of the support to be motivated to carry on. Sponsoring the mill there, Data Futurology. Real big thanks to Felipe and his podcast. They're organising all the techie stuff for me. So this video will be going on YouTube. I think it's kind of live there now. If anyone wants to post the link, it'd help in the chat. And I think with what we'll do today, there's a chat you can see if you're used to Zoom, and I think there's a Q&A somewhere, which I'm struggling to actually activate myself. So if there's any questions, type them in the Q&A, and I'll hopefully be able to find them at the end, and we'll go through them now. The talk could go on anywhere between 30 minutes and an hour and a half, kind of depending on how much I rabble on. I'm kind of probably renowned for kind of talking a lot, but we'll see. So, but it will be recorded, so if you want to leave, don't worry, it will be on YouTube. So, going back to our sponsors and Data Futurology, is Monica around to say a few words about what Data Futurology is up to, the Advancing AI Breakfast Series. Are you there? Anyone? Oh, no. Anyway, I'll mention it then. So Felipe is running a breakfast series starting pretty soon, which is, I think it's every 1 day a week in the morning from 8:30. You click on this link, it will take you to go aibreakfast.datafuturology, and there's lots of interesting talks there. There's quite a few. I haven't counted them. Looks to be about 8 or 9 every week. The first one is next Tuesday, the 9th of February. So join in, it should be fun. And one thing I noticed that's a bit hidden in Data Futurology, if you click on the YouTube link, there's a YouTube website. Well, you can see there we are now. We're currently live on their YouTube channel. But if you click on the video link, there's a whole bunch of past talks that you know, if you've got time, you should find really useful if you're into data science. Okay, so back to the presentation. Bit of background about me for those who don't know. You know, for the past 6 years, I think it is now, I've been running the Data Science Melbourne Meetup Group. We've got over 13,000 members. It's, you know, one of the biggest, if not the biggest, kind of city meetup groups on data science in the world. My kind of background in data science came when I did my doctorate in AI in the 90s. So I did a mechanical engineer. I was a kind of engineering doctorate and kind of veered towards AI, which I'll talk about it shortly. Currently, I use my kind of skills I kind of might have to build models to trade cryptocurrency. That's what I'm doing at the minute, and other markets. Connect with me on LinkedIn. Happy to join in with anyone. And if you've got any interesting projects, just that, you know, I might be able to help out with, just let me know, because the cryptocurrency is not always gangbusters. Okay, so basically a talk outline of what I'll be going through today. So I'm going to take you on a journey. So I'm going to describe basically linear regression and how that works, and then take you on a journey on kind of how that algorithm has evolved and kind of, I guess, grown, mutated to get more sophisticated, and kind of ended up, you know, with kind of neural networks. But it's kind of very interesting evolution, which once you understand how it works, it's not that complicated. We'll then move on to kind of another branch of algorithms, or another part of the family tree, which, no pun intended, are called tree-based algorithms, so decision trees and the like. And finally, I'll introduce a couple of tricks that basically, regardless of what algorithm you're using, will improve or should improve their performance. They're known as bagging and boosting. So there we have it. So there's a bit of a backstory to kind of my approach to things. So as I said, I was a mechanical engineer in the early 90s, dumped with doing a PhD on neural networks. So there was an engineering problem, and they decided, oh, there's this new thing called neural networks that's going to solve all our problems. Can you use that? It was like an engineering control problem. Can we use neural networks to self-learn a control system? That was great. Now, problem was, I was in an engineering department. No one knew what a neural network was. I certainly never heard of them. So I kind of dumped in at the deep end. I was an engineer, not a statistician or a computer scientist. And oh, geez, okay, let's start reading. So I read lots of papers. It was clear as mud. There's a lot of papers with pictures of brains, axons, neurons. What's that? What on earth's that got to do with it? It's a computer code. I really don't understand that. So I read lots of papers. I thought, okay. And then there was a decision made. I'm going to have to do some neural network stuff. So I could either do one of two things, which was buy a MATLAB license, which we couldn't afford. It's about £800 in the day. Or the more exciting option to me was code my own neural networks. So we kind of got a free Fortran compiler, and I was just kind of left to write everything myself. So I kind of had to then write a neural network. So I kind of scrammed together all these papers and kind of managed to derive what's called the backpropagation algorithm, which is how neural networks work. And just to save you the hard work, this has been on my student site for 20 odd years now. So if you go to philbriley.com, this was what eventually took me a year to understand. Now, this is the mathsy stuff. And I'm not going to talk about that because I don't think it's that important retrospectively. So that's the algorithm itself. So I wrote some neural network code that worked. Sorry, I wrote some neural network code that worked. So as academics do, you make up some synthetic data sets and see if your code can solve it. So I kind of did, y equals x squared. So, and stuck that into my neural network, and surprise, surprise, it works. But I thought, I still don't understand. I know the algorithm, and I've made up some synthetic equation because the paper says a neural network with enough hidden neurons can solve any equation, any problem. But I didn't understand. It wasn't clear what's happening. Now, what made it all of a sudden clear was when I started looking at pictures, and the penny dropped as to exactly what was going on, and it was that penny dropping that essentially kind of led me to where I am now. I think I kind of know what's going on. I know the problems, and I know what to avoid doing. Right, so I'll start the presentation. So that's the backstory, and I'm going to take you on the journey. So this is ice cream company, and they've got a kind of a problem. They don't have refrigerated kind of ice cream vans. So what they've got to do is they can only make enough ice cream that they're going to use that day, because they can't. The guy there, number 41, once he's finished his day shift, he can't take it and refrigerate it. So they've just got to produce what they can make, what they think they can sell. So there's two problems there. A, if they don't make enough, they're going to miss out on profit. If they make too much, it's going to go to waste. So this is a problem. So the current system they used was they just take, how many did we sell yesterday? We think we'll sell the same tomorrow, but we'll add a bit on just in case there's a bit more demand. Now, there's this Jane. Jane's down in the bottom right-hand corner. She was taken on as an intern, and her problem was to kind of, is there anything we can do to fix this problem? Is there any way we can better estimate how many ice creams we're going to sell, so we don't have any wastage and we won't miss out on profit by not producing enough? So Jane, in a little thought bubble there, kind of think, oh, okay. And the anecdote from the kind of the sellers was, we sell more on hot days than we do on cold days, and we sell more in summer than we do in winter. So Jane took that information and she kind of thought, oh well, yeah, I kind of seem to buy more ice cream on hot days, so I'll find the daily temperature. So she went kind of scrambling around, found some data on how hot every day was in the last year, and she kind of got their ice cream sales. Now, being astute, she only took the sales where they had stuff left over, because if she'd have took the sales where they ran out, that is not the true sale. It's kind of what's called a censored observation. So she says, in order to predict what we really would have sold, I'll just take those records. So Jane got to work on this task, and she stuck all her stuff in Excel and discovered some interesting things. So what I'm going to do, if I drag this over, so you can see it, this is what Jane discovered. So this is her Excel sheet she put it in. So she plotted the temperature on the x-axis and plotted the ice cream sales on the y-axis. And she kind of noticed they all seem to line up in a nice straight line. So she's thinking, oh, okay, so pretty well this is telling me that if I know what temperature is, I should be able to tell how many ice creams we're going to sell. It's okay. She said, well, but temperature's in degrees, ice cream sales is in number of ice cream cones. How am I going to convert one to the other? And she said, oh, when it's 0 degrees, I sell 0 ice creams. When it's 10 degrees, I sell 200. When it's 40 degrees, I sell 800. It looks as if there's some kind of linear relationship there. So she stuck it in Excel and created the Excel sheet you see here. So you've got temperature on the left, which is going from 0 to 40, and then the sales. the actual sales. And she said, this, I know sales equals something times temperature. How do I find that something? So she's kind of produced a little widget like this and put a little formula in Excel. And if you look in the top right here, I'm taking this, I'm guessing at a gradient, or what is that multiplying factor, and saying, that is going to convert temperature to sales. So she got this little widget and she said, oh, there we go. So temperature times 20 equals sales. That's great. So what she's done there is, so I'll just turn the sound off my phone. What she's done there is built her first kind of machine learning model. She specified sales is some function of temperature. That function is we just multiply it by some number. And that number in this case is 20. What she's also done, you see that there's gaps in the middle. Those were the records she deleted because that was when she didn't sell enough. So she can now estimate what they really would have sold on those particular days. She compare that with what they actually kind of sold when they ran out, and she can estimate, how much money they were losing. So this is Jane. She's built her first machine learning model. Now there's two bits to this model. There's the what, which is, it's the equation, sales equals something times temperature. And then there's the how. And the how is, how do I find that something? How do I find 20? How do I know what the number is, or the coefficients of my equation? And she's done it with a nice little widget here, like that. So this is kind of not really machine learning, this is human learning. She's using her eye to spot when a model looks good. Now then, she was feeling pretty good about herself. She goes, okay, now I've modeled ice cream, let's have a look at icy poles. So she did exactly the same again. And she just had initially she just had this one coefficient. And she kind of found a close relationship. So it's not working. It's close, but not very close. So what she then realized was the equation is really, it should be, there's this constant. When I'm at 0 temperature, 0 degrees, I actually sell about 100 icy poles. So I'll create a constant to add on. So that is the constant. So if we go like that, so the equation now becomes sales equals 20 times temperature plus 100. And you can see the Excel formula there. It's basically, it's what you probably all know as Y equals MX plus C. So sales equals M times temperature plus C, and it's the M and the C that kind of define that equation. Right, so now she's kind of modified, she's improved her initial algorithm to add this constant, so she's kind of made it a bit more flexible. And now she moves on. She says, right, I can model icy poles. I want to now model lime-flavored icy poles. So she got the data just for lime-flavored icy poles and plotted temperature against how many they sold. And then she said, oh dear, that's not the nice straight line I was expecting. Look, I can fiddle around with my knobs now, but I can't get them to line up. Which set of coefficients is the best, right? So she's now got another problem. She said, I can't do it, but I need to somehow define. I need to define a metric that tells me what line is best, because my eye it doesn't line up perfectly. So basically, she realized every prediction, whatever line she fits, there's always an error on every single day. Every single day's got an error. So if we look over on the left, the current prediction, sales there is 84. The current prediction based on this line, or these two coefficients, is 95, which gives you an error. So she needs an error function. She needs a metric that tells her the overall error over all the days, and she will choose the kind of coefficients that give her the least wrongness, which solution is least wrong. It's not, and because some errors are positive, you'll see here some dots are below the line, some dots are above the line. The errors can be positive or negative, but a positive error, whether you're plus 10 or minus 10 off, it's kind of, they're equivalent. You don't want to be just plus and negative errors are essentially an error anyway. So what she did, she took the absolute value of the error. So that's here, absolute value, and then just summed up all the absolute values. And that's the sum of all the absolute errors, is her error function, or it's commonly called, a loss function or a objective function. What function is your line trying to minimize? So if we say here the error is going up, so if we look at the sum of, they've been in orange, sum of absolute errors. As we play around with these coefficients, we should get to a point where it keeps going down and then it goes up again. So about there, if we change the offset one way, the error goes up and goes up. So there's a kind of one point in the middle where it's minimized the error. So that is sort of another enhancement of our algorithm. Rather than eyeball it, because she knows her data is not always perfect, she's decided we'll define this overall metric that tells us how good our error is. Okay. Now the one she chose was, this is kind of an aside here. The one she chose was absolute error. Now, common one is the sum of the squared error. So if you square an error, it kind of makes it positive. So you don't have to take the absolute value, and you take the square root of that to get it back to kind of the same scale. So taking the squared error is very kind of common to do, and another reason is not just that, is because it's easy to differentiate a square. So when you kind of fits in with the maths of how you find these solutions. But the problem here is you've got some noisy data. So this is her ICPOL sales. And 2 days, someone wrote down in the spreadsheet, they put an extra 0 on, say, and you've got these that when they wrote on the paper how many they sold, they made a mistake. So you get these noisy points. The problem with having such extreme points like that, because you're squaring the errors, the line of best fit is pulled towards the error, because having less, when your error is big, the squared error is even bigger. So you kind of line gets kind of pushed towards points with big errors. So I think that is the current best error. So if you see here, the errors going up. You see it's 487, 486. It's going down. 484, 495. Now it's going up again. So it's going to say that's the best solution. So just a warning that if you've got lots of extreme values, that it will push your solution towards those values. Okay. So we'll forget Jane for the time being and just move on to some more enhancements. So one of your data looks like this. So it's kind of got a kink in it. It's linear in the first bit, and then it's linear but with a different gradient in the second bit. How can we deal with this? The linear regression wouldn't be able to wouldn't be able to handle that, because it wants to stick one straight line. So basically what evolved here was what's called regression splines. So there's the algorithm is probably known as Mars. multivariate adaptive regression splines. If you do kind of R or Python, it'll be called Earth, because Mars is a trademark. But basically what happens here, we've got the same two kind of, we've got two linear regressions with what's called a knot. Now the knot is just a point where we say anything below that point, let's see if I can get this to work. Anything below that point, use the first regression. Can't quite do it. This is why we need machines. Gradient. Yeah. So we've got to find two sets of regression coefficients, a position where the knot is, and there we go. Essentially, with a variance of linear regression, we can now bend our curve a bit around the data. Okay, so that's kind of one evolution of linear regression, multivariate adaptive regression splines. Now, what if the data is a bit like this? So no data is ever in a straight line. It just doesn't happen. So for example, it was kind of S-shaped. At a low temperature, you sold less, and you got to a point where you sold zero. It don't matter how cold it gets, you never sell anymore. People just aren't buying them. And then, at a high temperature, it kind of increases, but it gets to a certain point where, whether it's 30 degrees, 40 degrees, or 50 degrees, people aren't going to buy anymore if it's 60 degrees, because it's just hot and they're going to buy what they want. But if with our linear regression, we've got a problem. Just by having the y equals mx plus c, we can never really accommodate that kind of non-linearity, that curve. So you see here the actuals there, and we're just doing it as linear. So what can we do about that based on kind of our linear regression knowledge? So it's pretty simple actually. We use the same initial linear stuff, and then we just stick it through a non-linear function. So if you look at the formula up there, that's the first bit of it. I'm just finding the gradient and the offset, and I'm times my value by the gradient and adding the offset. And then there's one further step. So we found the gradient and offset, and then one further step is we just pass that through what's some kind of function. In this case, it's a logistic function, which is 1 over 1 to the exponential of 1 minus whatever comes out of the first bit. Okay? So let's see what happens here. So I've got to now play around with these numbers to get that line to fit. So there we go. So I've now done logistic regression, where I've managed to kind of get a good fit, and it's just one little function added on to the end of linear regression. That's great. So now a lot of you probably have used linear regression for other things, and it's great for classification. So you probably use for probability. So what's the probability of buying an ice cream? Somewhere between 0 and 1. So one reason it's good is because it's bounded between 0 and 1. It can never go less than 0 or above 1, and it can act as a kind of gate or a decision boundary. So the gradient's really, just by using linear regression with the logistic function, if you make the gradient really high, essentially it can act as a switch, which basically you'll get to a certain temperature and say, okay, we'll go from 0 off to 1 on, and that's useful, a useful thing to know. Right, so that's the end of as far as I can take it in Excel. As much as I don't love Excel, it's got its limits. So we've kind of done logistic regression. Now, what if we want to model something like x squared? So this is a neural network. This is software I developed called Tiberius, which is free to download and use. And I'm going to show you how neural network, how the next evolution from logistic regression to a neural network works. Okay, Samara's just connecting. It's a sigmoid function. There's a lot of functions you can use: logistic, sigmoid, hyperbolic tangent. But let's not get into the nitty-gritty. So this is X. This is kind of like our sales, our ice cream sales. We've got X on the, got say temperature, that's sales, but it's kind of in a kind of, it goes up when temperature's low, up when temperature's high, and it's like an X squared function. So this is linear regression. This is essentially what's happening. We've got X, which is temperature. Bias is just the one, which essentially is which accounts for the kind of constant. We've got these two black lines joining to this blue node, and these black lines essentially the numbers. We're trying to find the coefficients. There's a bit of stuff up the right. You don't need to worry about that for the time being. So we try to find a solution to that. So we can't solve y equals x squared just using linear regression because it's just not possible. What we can do, we make it logistic regression. Bear with me. And this is the kind of backprop. This is the learning algorithm going into force. It's kind of trying to find a good solution. You can see there that just because there's only one logistic function, that's the best it can do. It's done its best. It's found a solution that kind of solves half the problem. Now what we can do, we can add two neural networks. Sorry, two hidden neurons. That's what I'm going to call them now. Two logistic functions. Let's see what happens here. So it's kind of iterating away, learning and learning and learning. Let's try and minimize this overall error. And there you see, let's speed up the learning rate. It's kind of getting close to approximating y equals x squared. Now how the hell is, so this was where I was at with my PhD. I'd written this neural network, it solved y equals x squared, but I was none the wiser as to how the hell it had done it. I knew the algorithm works, I knew the backpropagation found me the best solution, but you know, it didn't help me comprehend what was going on underneath. So this is how it's actually done it. So we've got, this is the network now. So we've not got, this yellow dot is say logistic regression, but we've got two of them, and we add them together, weighted appropriately to give us the solution. So essentially what happens is one of those neurons is giving the purple line, one's giving the red line. And when you add those together, you end up with this, y equals x squared. So that's what the neural network's done. So we can do it here. This is called kind of initializing the neural network. You just start off with random numbers, and it gives you a random solution. And then when it starts to learn, it tries to improve that solution. Now, this is kind of getting more in here. Is it going to get stuck in what's called a local minimum? Because both bits of that logistic curve are doing the same thing. I'll bump up the learning rate. And it's not going to do it. So I'll start again. Come on. What's happening now? Okay, it's still not going to do it. There we go. That demonstrates why learning in neural networks can be problematic. But that's another talk. Okay, so that's kind of how neural networks kind of work. They're just essentially a few logistic functions kind of combined. Now, a load of neural networks are pretty versatile. They can solve something here called a really complicated function. Okay, so this is a similar data again. So rather than kind of sales going up linearly with temperature, there's kind of this weird shape where they do lots of different things. Now, if we try to solve that with linear regression, you know, physically can't do it. It can't kind of model all the quirks of the data. If we made it a bit of a neural network, so we'll give it a bit more flexibility to bend around, and let's see what happens there. It's struggling again. It's kind of really struggling. Let's reset the weights and start again. It's really struggling. Let's reset again. Right, it's hard to find. It's hard for the algorithm to find a solution. I'm going to persist. I'm going to add more. There we go. So I've given it more flexibility, and it's getting kind of a bit closer to that, to what it needs to be. Now you can see from this red line that it's just an addition. It's just a sum of a bunch of these S-shaped logistic functions or sigmoid functions or hyperbolic tangent functions, and it's just kind of added them together. Now, it can actually solve that problem, but it needs a bit of help. So I'm going to try and help it. Oops. Essentially by it's by the help it needs is it's got to simultaneously find all these coefficients at the same time, and it can't do that. Some have got to kind of jump. You can't do them by gradually changing them. Some have got to massively change. So you can see there how it's getting better at solving it, and that's 1, 2, 3, 4, 5, 6. That's got 8 hidden neurons. Now if I try again, I should be able to get it even better by essentially what's called seeding. There we go. So now we've got all those hidden neurons with just one variable, and we've been able to learn a pretty weird function. And that is how a neural network works. Okay. Get rid of that. So go back to my slides. So that's what I just talked you through. That's where we were. So this is a neural network. That's logistic regression. So before I kind of showed you, it was just temperature trying to predict ice cream sales. Now you don't just have to have temperature. It could be temperature, what day of the week it is it raining? So there's a whole bunch of inputs that can go into the prediction, and the output is your prediction. So that's a logistic regression. And that's essentially a neural network. It's just a whole bunch of logistic regressions added together to kind of spline fit. So it's just a bunch of spline fitting of these S-shaped things to come up with the complicated patterns we've seen. Okay, a little aside here. So that's the what. Now, I think I said before, it's the what that's important. That's, you know, what they do, how they do it, in essentially how would we find those coefficients, is left to the clever people. There's a whole bunch, say for logistic regression, there's a whole bunch of methods of how these coefficients are found. If you're interested, just Google a guy called Tom Minker. This was a paper from like 20 odd years ago, but it will give you an appreciation of the different ways. But we're going to leave it there. And then the neural network uses a backpropagation update rule, and I've showed you the code. That's kind of all fancy stuff like this, and the code's on my webpage. But it's not important. I kind of genuinely believe, go through the algorithm and see if you can follow it, but don't get too worried if you can't, because other people have done all the hard stuff for you. So that's the kind of regression type, linear regression to neural network family tree, kind of branch of the family. And there's another branch called decision trees. So this is kind of a different way of solving a similar problem. So these techniques so far are kind of suited to well-behaved patterns. So it's another problem here. So you've got age and income. Maybe this is credit risk problem. Depending on the combination of age and income, you're either likely to pay your credit card bill or you're not. So you're either a red dot or a blue dot, and the algorithm's got to kind of find some kind of line between the two. And a lot of patterns are nice and continuous, and that's doable. But say linear regression and logistic regression will struggle in some cases because data's just not like that. A neural net not so much, because I've just shown you it's got a lot of flexibility to work its way around these things. So this is the data. Same kind of thing. There's different rules of age and income to decide whether you're a good risk or a bad risk, or a red dot or a blue dot. Now we can just eyeball that and kind of say it's quite clearly solvable just by partitioning it up. Would need a different technique to do it. So this is where decision trees come in. So, for example, we start off with the whole population, all those dots. We can fit a line down there that says we find a value of age, and we've kind of scanned all these ages and said, is there an age where we kind of get proportionally more red dots on one side of the line and proportionally more blue dots on the other side of the line? And we found that value, age, and we kind of then decide we'll define it as low age and high age, and we split you into two. We then take each of those partitions of the data, and we just look at the high age group and we say, okay, given that you're a high age, is there anything else that can divide you into being more red dots on one side of the line than blue dots? So we then look at the income, another variable, and it said, okay, yeah, if I just look at that subgroup and find a value for income, I get all reds on one side of the line and all blues on the other side of the line. And then we look at the other side of the line, the low income group, we find two other values. So that's kind of essentially how a decision tree works. It's basically recursive partitioning. It partitions the data up into smaller and smaller groups and find rules. And the way the algorithm works, it kind of just scans all the data you've got for the data, for the kind of partition, the subpopulation you're currently looking at. And it finds out what predictor, which bit of data and what value of that data will best split the data into kind of diverse groups where there's kind of relatively more of one set than the other. That's pretty well all you need to kind of, just as a concept, you need to know about the tree learning algorithm. Now I've got some code here that will kind of show you how all this works. Now I'm kind of hoping you can all still hear me. Can someone type yes if you're still there? Because I cannot. Yes, thank you. Right. Thumbs up if you think this is this useful. Yes, no, rubbish. Anyway. Right. Thank you, Ed. All right. So I'm going to show you how a decision tree in practice works in R. So this is R Studio. So R is a kind of a programming language that can do lots of modeling, lots of data preparation, lots of stuff. You probably, if I'm guessing, a lot of your students are more familiar with Python. Well, I'm from back in the day when Python didn't exist, so I kind of learned R. So, as I said earlier, these clever guys have come up with these algorithms that that build your tree for you, build your neural network for you. They come up with the coefficients, and you see, just going back to this code, the code I've highlighted there is essentially building the model. I'm just saying, use this library called random forest, pass in a few parameters, which essentially, what is the data? How many trees do I want? So I'm using a thing called random forest with one tree, which is essentially just a decision tree. And terminal nodes. How big do I want to grow that tree? How many times I want to keep partitioning and partitioning. So you can partition and partition and partition until you've got only one person left. And he's got a unique set of rules that only he will kind of obey. So one rule might be, what's your name? My name's Phil. Okay, you're in that set, but that's vastly overfit. The rest of the code is just some data processing and plotting. I'll run it, and I'll then talk you through what it's actually doing. So what I've done, I've generated a kind of synthetic data set with two variables, X and Y. And I've said, based on your X and Y combination, you're either above this green line or below this green line. So think of it as like maybe age and income. If you're if your combination of age and income is above that green line, you're I don't know, good credit risk. If you're below, you're a bad credit risk. And I'm trying to kind of solve that equation. I'm trying to solve that problem using a decision tree. So I'll just go back a few plots. It's finished now. So the ground truth is the first one. So that's my synthetic data. I've generated all this data and colored. They're all random points, but I've colored them either red or green depending on what class they are. So the data set's got 3 columns: X, Y, and class, which means either red or green. Now I've then gone through essentially a loop here in your code. I say build trees with an increasing number of terminal nodes. So with just 2 terminal nodes, so it kind of can like partition the data just once essentially. It's kind of struggling. It can't solve that kind of what's essentially a nonlinear problem. As we make the tree more flexible, you will see it gets better and better. But you can see all the kind of lines are square. It's done it in kind of linear chunks. And as we kind of build the tree deeper and deeper, it can essentially come up with something nonlinear, similar to what a neural network would do just by using a couple of sigmoid functions. So that is, Ed's just learned, excellent. Nice one, Ed. What university is that? No, they taught R anymore. Okay, so that's basically how decision trees work. Now, that comes kind of to the end of the kind of algorithms work. Now I'm going to talk about finally these 2 techniques I mentioned earlier. Sorry, I lost my these 2 techniques I mentioned earlier. There we go. That were tricks of how you can improve a model. Now the first one I'm going to mention is bagging. Now bagging can be used in any algorithm, whether it's a linear regression, neural network, decision tree. It's kind of an overlay. And before I tell you what it is, I'm going to just run this code and talk you through what it's done. Right. Right, so that's finished. So what this code is just a few lines of code. I've generated a synthetic data set. And it's like this, the straight line version of the sales is some function of temperature. So I've got one value x, which is temperature, and the y-axis. I'm trying to model how many ice creams we sell. Now I've added some noise to that data. So there's not many points, and it broadly fits on that. The green line is the kind of noiseless data. The blue line is the data I've been given. And the model I'm trying to fit is actually a polynomial of degree 10. So I'm giving it a really flexible equation. So a polynomial basically is linear regression is y equals mx plus c. Polynomial will be like y equals x something times x squared plus x something times x plus c, or the 10th order or 10th degree will be x to the power of 10 plus x to the power of 9 with a bunch of coefficients to fit this bendy line. So it's really flexible, and with just a few points, because of the noise, it's trying to model that noise. So the first, think of this as I'm giving a data set to, say I've got 1,000 of you. I've given you all a very similar data set, but slightly different, because all have got different bits of noise. I'm giving you random samples of the same data set. Noise. So the first graph there is custom. One of you will say, okay, based on the dots you've given me, I'll fit this red line. Someone else will say, okay, based on the points you've given me, I'll fit this line. So there's six different people there have given their 6 different versions of the truth based on the data I've given them. Another 6. So in this case, I've given it to 2,000. So what do I do with those 2,000 kind of predictions? Well, if I just average them, I get the perfect straight line that starts the kind of noiseless straight line. So basically what bagging is doing is it's building lots of models with the same algorithm, well, slightly different subsets, because we know the data contains noise, and averaging out that noise. It's essentially what the concept of bagging. Now, if you used all the data on one algorithm and there was no kind of stochastic randomness in it, you'd always get the same solution. So say you had what I showed you earlier about, if there's some outliers in the data, those outliers will always appear in that algorithm, and it will always try to be biased towards those outliers, which essentially are noise. If I gave you random subsets of that data, a lot of, if I gave you a 10% sample of that data to 10 different people, 9 of those people probably wouldn't have that noisy point. So they would get kind of a different version of the truth. And that's essentially what noise is, what bagging is. Now then, move that over there. So what bagging? Bagging stands for bootstrap aggregating. So essentially what it is, the name is what I've just described. You take bootstrap sample is basically you take all the data and take a random sample of it. So you don't take it all, you take a random sample of it, and in some cases you won't, so that's the number of rows, the number of records. In some cases, you won't give the same number of predictors as well, the number of columns. You'll say, I'm not giving you the temperature, I'll give you what day of the week it is for this model, whether it's rained. So you can kind of randomly sample on the records themselves and the columns or the predictors. And the aggregating is essentially what I did at the end. It was just adding them all together. So a typical kind of the kind of bagging algorithm you'd probably all be aware of is random forest, where it just builds lots and lots of decision trees and averages them, and you kind of end up with a solution. It literally can't overfit, because not one algorithm is not looking at all the data. Each one's looking at kind of subsets of it. So each one of those individual models, when you aggregate them, it's impossible to overfit because you just can't. And that's what I've just showed you. So yeah, random forest is a bagging algorithm. So the base learner is the tree. You build individual trees. You can just keep growing and growing and growing until no further splits are possible. These trees are very overfit. And you know, you should get almost a perfect model, like I showed you with that kind of non-linear y equals x squared type problem. You build lots of trees on average. That's pretty well the bagging trick. Now, it doesn't have to be a tree. You can bag with, I just showed you that, you can bag with polynomial regression. You can bag with any algorithm. One interesting thing is if you bag with linear regression, you essentially end up, if you average a bunch of linear regression coefficients, you essentially, the equation is a linear regression, but with a different set of coefficients. So it still is linear regression, but what you find happen there is what's called regularization. So each individual linear regression has not seen the whole data, so it won't fit to any outliers. Well, you know, some will, some won't, but they'll kind of get averaged out. And what you'll find is that the coefficients of the average linear regression won't be as extreme, and it will kind of give it's a way of regularizing or not overfitting linear regression. But there are other techniques that do just the same thing, called like ridge regression. Okay. Now the final thing, this is what I'll just show you. I'm going to talk about, my final thing I'm going to show you is boosting. Again, I'm going to run the code and then talk through what it's done and see if you can figure out what it's doing. So, right. This is, now boosting is again a technique that can be used on any base algorithm. What I'm going to do with this is use a neural network with 3 hidden neurons. Now, let's see what happens when I run it. So what we're doing here, I'll talk to the graph. So I've set my kind of ideal function there. So I'm trying to solve this sine wave with 3 hidden neurons, which I know it can't do because there's just not enough hidden neurons to get that function. So the whole concept of boosting is you kind of build one model and learn the best you can, and then you say, okay, let's take what you've done, but what I'm going to do now is concentrate on what you've got wrong, and I'll build the next model on what you've got wrong. And it kind of keeps going and going and going and going. And each step, it focuses on where it's going wrong. Now, this is a bit of code I wrote, and I just took a description. Someone just verbally told me what it was. There are big bagging algorithms I could use, but I thought I'll just take the base learner, apply the concepts, and see if I can get it to work. So I'll explain these graphs. So we've got a test set, and we've got to get all the reds above the green line in the top left plot and all the blacks below the green line. And it does that by building a series of models where one model kind of learns based on where the previous kind of model got it wrong. And as you can see, it's through time, as the number of models increasing, the graph on the right is universal approximator, Hornick's theorem. Thanks, LP. It was called something else when I remember. It was called some Russian guy's name. What was his? I'll remember his name. It wasn't Hornick. Anyway, so as it's going down, it gets less and less and less and less. The error's going down, and you can see visually it's something. So how is it actually doing this? So the bottom left graph is essentially taking all these previous previous models and saying where are we still getting it wrong. I'm only going to train on those points that are getting it wrong. So the dots in the bottom left corner, from the training data, the ones it's using to build that iteration of the model. So you can see now we've built 555 models with 3 neurons, and it's gradually getting there. You know, so that's essentially what boosting is. It's the kind of, I'll stop that. It's focusing on where you're going wrong. So I've got someone that will explain that a bit more graphically in a minute. But now we'll do the same again. Kolgomorov's theorem. I think he had another theorem about neural networks can learn any universal approximation. Right, so I'm going to do exactly the same again, but rather than use a neural network, I'm going to use a decision tree. We'll put 3 terminal nodes. So it's kind of called a weak learner. So a decision tree with 3 nodes can't really learn a complicated problem. But if we do this boosting, you can see how it gradually solves that problem by focusing on where it's going wrong. So there we go. And you can see the tree algorithm seems to be a lot more efficient than the neural network, because the neural network learning is a lot more difficult. There's a lot of local minimum going on if you're into that kind of thing. But you can see in the top left, the solution is square, because we're using kind of this partitioning. It's not it's building it in chunks. You're either to the left or the right. You're either to the left of the line or the right of the line. And there you go. So you can see there. Actually, the overall error is going up now. If I increase the number of neurons, if I make the base learner more complicated, more terminal nodes, it should solve it a lot quicker and a lot less chunky. Right. There we go. So that is essentially what boosting is all about. Finally, I'll show you the logic. I'll talk through all that, right? So go back to the neural network. So say we're trying to solve this sine wave with 2 hidden neurons. We know we can't. We know at best, two logistic functions can combine to add up to, they can just essentially model one of those features, one of those kind of bits of the sine wave. And it can't do all simultaneously. So what we do is we hope that our initial neural network with 2 hidden neurons will come up with this solution. And that's kind of where it's at. And then if we calculate the error on the rest of them, it will look like this. So then the bottom line there. So then we try to learn the error. So it's kind of going to ignore, it's going to focus, it's going to make those 2 neurons now move on to the next feature, or this next dip, which it will gradually move along, and then the error will become that. So that's the kind of second model that's learned the second feature. And it will gradually kind of boost along, focusing on where it's gone wrong. That's my code. So that essentially is all I've got for you today. Now, I can't see anyone, I can't hear anyone, and I can't see the Q&As. So if you've got any questions that you want answering, can you type them into the, into the chat? Right. Kerry, can you give us a brief description of the backpropagation method? So Kerry, I showed you, if you go to philbriley.com/code, you'll see the derivation. Hey, that wiki has a C also called Glomerov. Okay, thank you. I knew there was some guy called Glomerov. I could never pronounce his name, but I presume he's Russian. Are these scripts available on GitHub? No. What I would recommend you to do, the ones I've shown you, I wrote those based on a description. Am I still sharing my screen? Right, what I will do is I'll encourage you to kind of just look at that and come up with your own. And if you're struggling, just ping me, and I can help you out. But I would encourage you to, if you want to really learn about kind of how they work, try writing your own. You don't have to write the neural network algorithm or the decision tree. You just use the package, but you kind of put a wrapper around it to selectively do particular stuff. So I'll show you am I still sharing my screen? No. That answers the code question. Right. Okay. So it's 2 o'clock, 6 minutes past 2 now, and can't see any more questions. So what I'm going to do is leave it there, and hopefully you all had an informative hour, and you can get back to your lunch. So I'll call it a day there, and hopefully we'll be having another meetup soon. So if you're a potential presenter, let me know. We'll set up a webinar. If you've got anything interesting to tell us about, let us know. Okay. Thanks all, and we will see you shortly, hopefully in person.